In this video, we're going to be talking about the normal distribution. So we've already discussed measures of centers in spread. We've talked about the mean, the median, and the mode. We've talked about range, interquartile range, and standard deviation. We've also talked about two different types of distributions. We have skewed distributions. You can have skewed to the left or skewed to the right, whichever direction the outliers are in. And we also have symmetrical distributions, which are approximately symmetrical. They don't have to be 100% symmetrical. And those are the ones we're going to be focusing here on with our normal distributions. And as we've looked at these distributions, we've been looking at them primarily as histograms, with the bars representing the height and different class widths at the bottom. And we notice that these symmetrical distributions occur most frequently with measurements and test scores and other naturally occurring phenomena, where most scores or measurements occur. Most of the people would have the same score or measurements, some a little higher, some a little lower, but there's about just as many high as low scores. All of these distribution graphs are histograms. Like I said, as the height of the bar, it represents the frequency of the occurrence. And in these normal distributions, most of the data values fall in the middle. So here's an example of a histogram of the verbal SAT scores for a recent freshman class at a small college. Again, you can see most of the scores fall in the middle. Everybody scores about the same thing on the test. However, there is quite a range of scores. They go to very high to very low. And we don't actually see the score numbers on here, but we still get a picture of the distribution. So instead of representing now with these frequency bars, we're now going to draw in a curved line to represent the data distribution. And you're going to sketch in, basically we start by sketching in a smooth curve, tracing along the tops of the frequency bars. And we end up resulting in something that we call a normal curve. And this is sometimes called a bell curve because of its shape. And there's been enough research done for many, many years in statistics to know that things that are normally distributed, that are approximately symmetrical, that we can predict that most people have about the same score with some high, some low, will all follow this type of distribution. So there's no such thing as a perfect bell curve, but we draw it that way because we have conclusions and analyses that we can do based upon the fact that it's approximately perfect. And when we do have a data set that is normal or approximately normal, we can characterize it by its mean and standard deviation. And what that means is, by just telling you what the mean and standard deviation of that data set are, you can actually graph the normal curve for that piece of data. So as we talk about standard deviations, the larger the standard deviation, the more spread out the curve and the less high the peak is. It's wider because there's less values in the middle, whereas, and therefore it's a little bit more spread out. There are more values to the sides of the middle. The mean in a normal distribution is always the point along the horizontal axis at which the peak occurs. Because these are symmetrical, the mean is the measure of center, and therefore it occurs in the middle of the curve. And in this case, you can see this is a normal distribution of grades that has a mean of 80 and a standard deviation of 5. And we're going to talk through how it is we can actually, just knowing those two pieces of information, the mean of 80 and a standard deviation of 5, how we can actually draw this curve, this distribution, and know what percentages of values fall between which grades. So as you can see, again, the mean falls right in the center of the distribution. So what else the peak represents, because it is a peak and because the height of the curve represents the frequency, that also represents the most frequently occurring value. So the mean, in this case 80, a score of 80, is the most frequently occurring score. More people score 80 than they score anything else. So as we're talking about how this normal curve works and how we can learn how to draw it, it's important to know some of the key, literally turning points of the curve. So as we start tracing the curve from left to right, we can see that initially the curve is concave upward. You know, if you think of a bowl, the shape of the bowl is pointing upward. So it's concave up initially. The curve changes from concave up to concave down at mu minus sigma. That means one standard deviation below the mean is where the curve changes. So in this case, our mean is 80, our standard deviation is 5. So at a score of 75 is where the curve is going to change from concave up to concave down. And it's going to stay concave down until we reach mu plus sigma. You know, again, this is symmetrical, so we would expect that if it starts to go concave down at mu minus sigma, at mu plus sigma, it would turn back around again. So 80 plus 5 is 85, so it's going to be concave down until we get to a score of 85. And then it changes back to concave up, and it's going to stay there until it basically touches the curve again at the end. So you can see here kind of a whole discussion of the whole process. At about 3 standard deviations below, if 80 is our mean, 3 standard deviations, 3 times 5 would be 15. 15 below 80 is 65. At 3 standard deviations below, it's practically touching the curve. At 1 standard deviation, the concavity changes. It changes above, back again at 1 standard deviation above. And again, it's practically touching at the horizontal axis at 3 standard deviations above. So at the left and right end, it gets closer and closer to the horizontal axis, but it doesn't quite necessarily touch. And that's the point where it's approaching 3 standard deviations away from the mean. So if we're going to sketch a normal curve, let's walk through the process of doing that. So we start by marking key points along the horizontal measurement axis. If we're told that the data is normally distributed and we're given the mean and standard deviation, then we can sketch the curve. That's the only 2 pieces of information that we need, the mean and standard deviation, after we've been told it's normally distributed. And I just want you to notice that as we're talking about this, we're going to say sketch and not graph. These are not going to be perfect. No one's going to expect that they're perfect. They're not 100% accurate representations, but they're close enough for the types of analysis that we do. So let's go back to our scores example. So suppose we know that grades in a large freshman course are approximately normally distributed with a mean of 80 and a standard deviation of 5. This gives us all of the information that we need to be able to graph this. We know it's normally distributed, we have a mean, we have a standard deviation. So our mu is 80, our sigma is 5. And we normally draw these in a box. Not exactly sure why they're always in a box, but we tend to draw them in a box. Label the top of this, normal distribution of grades in a large freshman class. And on the bottom, we're just saying that the bottom is representing the grades with a mean of 80 and a standard deviation of 5. So those are the labels we'd put on a standard normal curve graph. So the first thing we're going to do is mark the mean of 80 on the horizontal axis. And because we know that this is the center point, we're going to put it right in the middle. Then we start to identify and mark 1, 2, and 3 standard deviations above and below the mean to set our scale. So whatever paper you're doing this on, you want to make sure these are measured in the same measurement apart, but you want that 3 standard deviations to be pretty much over at the end. So the way we do this is we add the standard deviations. 80 plus 1 standard deviation is 85, 2 standard deviations is 90, 3 standard deviations is 95, and we do the same thing in the other direction. Standard deviation is 5, therefore our points are going to be 5 apart. And we can throw on a couple numbers, you know, another 5 at the end just to mark all the way out, because again, at 3 standard deviations, it's not quite 100% touching. So now we're going to sketch the curve, remembering those concavity rules. So we start close to the axis at mu minus 3 sigma. So 3 standard deviations below was 65. We start there, and we know it's going to be concave up until it reaches mu minus 1 standard deviation. And I recommend that you sketch this in pencil so that we can smooth this out later. So we know now at 1 standard deviation it's going to switch to be concave down until it gets to 1 standard deviation above, so from 1 below to 1 above. And then it's going to switch concavity again until it gets to mu plus 3 sigma, where it'll be very close but not quite touching the axis. And now we've drawn this normal curve. So the only thing left to do is kind of to clean it out a little bit. So we're going to smooth this out. You tend to draw these in chunks as you're getting used to doing this. I actually tend to start with the concave part, down part, going from mu minus sigma to mu plus sigma, and then add the tails on. But we're going to kind of smooth this out at this point, which is another good reason for doing this in pencil, because then it's easy to erase the previous one if you sketch your original one very lightly. So now we're going to talk about some basic characteristics of this normal curve. We've kind of touched on a few by talking about the concavity, but we're going to talk about a little bit more specifically. So we said the peak occurs above the value on the horizontal axis that corresponds to the mean of the data set. Again, that's because this is symmetrical, and it's going to be symmetrical about the mean. And the curve is symmetrical with respect to the mean. The curve changes concavity above the 2 points on the horizontal axis located 1 standard deviation from the mean. That's where it goes from concave up to concave down. And it practically touches, but doesn't quite touch, 3 standard deviations away from the mean. So what's important, and one of the most powerful things to understand about these normal curves is, because they're symmetrical, we can apply the same rules to these curves as far as data distribution to understand percentages and how the data lies underneath there. And we can do this using this thing called an empirical rule. It's a rule that's derived from practical experience. This is probably going to be very different for you from what you've probably seen in math before or science, where everything has to be proven. Again, this is not a proven thing. From one curve to another, it's not 100% true, but it's close enough for all of them that we use this empirical rule when we talk about the percentages that fall under the curve. So if the observations in a data set can be approximated by a normal curve, then approximately 68% of the values are going to fall within 1 standard deviation of the mean. So 1 standard deviation below to 1 standard deviation above, all of those data values are going to be 68%. So in our example, we were talking about scores. With the mean of 80 and a standard deviation of 5, that means 68% of all the people scored between a 75 and an 85, 1 standard deviation below and 1 above. 95% of the data will fall within 2 standard deviations of the mean, and 99.7% will fall within 3 standard deviations of the mean. And this is a picture that kind of shows that. And it kind of makes sense as you look at it, because again, the center, the peak, represents the fact that there are more data values there than out at the tail. So the fact that the peak is high in the center, 68% of our data values fall in that center piece, that kind of makes sense. That's a little bit over 2/3 of the data values. Again, if you look at the 95%, that makes sense as well. We only have 2 little tails left on either side of that. That's the remaining 5% of the data. And out to 3 standard deviations is 99.7%. That extra 3% that's a little beyond 3 standard deviations is because there are always, not necessarily outliers, but as we talked about with people's height, there's always that one really tall person, one really short person that needs to be accounted for. So how are we going to use this? We can use those percentages to be able to identify percentages of people or ranges of scores that occur in certain amounts. So looking at this example, if we have a verbal SAT score for freshmen at a certain college, it follows an approximately normal distribution with a mean of 550 and a standard deviation of 79. So we've got our mu of 550 and our sigma is 79. So we're going to use the empirical rule to find an interval of values within which approximately 68% of the verbal freshman SAT scores fall. So what scores, between what two scores do 68% of all the freshmen end up scoring? And that's what the question is asking. So the rule says 68% of values fall within one standard deviation of the mean, so we need to find out what values fall within one standard deviation of the mean. So we do mu minus sigma. 550 minus 79 is 471. Mu plus sigma is 629. So approximately 68% of the scores will fall between 471 and 629. Now we follow the same process if we wanted to figure out where 95% of the verbal scores lie. We know that 95% of the values fall within two standard deviations, so we calculate those, how far out that is, and that's what our answer will be. So mu minus 2 sigma is 392. Mu plus 2 sigma is 708. So 95% of the scores fall between 392 and 708. And again, we'll follow the same exact rule with the 99.7. Now we're following the rule that says 3 standard deviations of the mean. So we're going to calculate that out. 3 standard deviations away subtracted from the mean is 313. 3 standard deviations added is 787. So 99.7 of all the scores will fall between 313 and 787. So we can take this a step further and find out, how many students fall into those buckets. We know what the range of scores is, but how many students is that? So if there's 482 students, how many fall into that 68, 95, and 99.7 bucket? Well, those 68, 95, and 99.7 are all percentages. So 68% of 482 will tell us how many students scored in that 68% range. So we're going to calculate that. 0.68 times 482 is 328. And we'll do the same thing for the 95% and the 99.7%. And you'll see that 99.7%, 481 students, still is not all of the students. We had a total of 482. So let's take this one step further, because a lot of the time we're not just interested in finding out, it would be nice and simple if all the time we were just looking for information that fell in these nice predefined 68% or 95% rules. We're going to start first by finding out, still using those values to calculate some other types of ranges, and then we'll be taking it a step further as we go into the future to be able to figure out at any point along this curve what the percentage would be. So we're going to say that this information that we have here, this curve that we've drawn, is normally distributed with a mean of 70 and a standard deviation of 10. And this is the shorthand terminology. Just seeing that capital N parentheses 70, 10 tells us everything we need to know about this entire set of data. We could have 5 million pieces of data in here, and that one shorthand tells us everything we need to know about the distribution. So we're going to go in and fill in our numerical values down below, just as we've done before. So for example, we know the mean is 70, standard deviation is 10, so one standard deviation below is 60, another is 50, another is 40, and then 80, 90, and 100 above. So what if we wanted to now find out what percent of students scored between a 60 and 100 in this particular class? So what we're looking at is what students scored between these two values, or what is the area under the curve between these two yellow bars. So where these yellow squiggles are shaded in, what is the area under the curve? That area represents the percent of students who scored between a 60 and 100%. So we can do that using the empirical rule just by subtracting and adding some of these pieces together. So for example, we know between these two red bars is 68% of the data. So what we still need to figure out is what is left over in this little tail end. And keep in mind, we know that this is 68% of the data, and going all the way out to the end is 97%. 99.7% of the data. So we just need to figure out what's down here in this tail end to be able to determine what's left over. And the way that we're going to do that is to say, if from this yellow bar all the way down to here is 99.7, if we subtract out the 68 in the middle, we get this tail plus this tail left over. So 99.7 gives us the two triangular tails on the end here. But we don't want both triangular tails. We only want the tail that's on the right here. And because it's symmetrical, we know that this is exactly half of the two of them. So if we divide 99.7 minus 68 by 2, we're going to come up with 15.85%. And that is the area under this tail of the curve. So now if we add together the 68% and the 15.85%, we find that the total area between 60 and 100 is 83.85%. In other videos, there will be examples of specific problems from the textbook that talk about that.